Well, you made it to the last video in this lecture. Great job. We'll just do one more example. So we've got our vector field f, and we want to take the surface integral of f over this particular surface. And S, for the first time in this lecture, is going to be a closed surface. So it's enclosed by this paraboloid and then the xy plane. I've drawn a picture for you here. It's closed, but we're told it has positive orientation. And so that means we want the normal vectors to point out of S, not into S. So the orientation looks like this. If it had negative orientation, then they would all point in like this. That's not what we want. We want to go out. So that's the game. And so what you want to do here is what you should do. The surface integral of f over S, you can write as the surface integral of f over S1, that's an S there, not a 5, plus the surface integral of f over S2. And now we're going to just dive into S1. So S1 is the paraboloid, at least the way that I've labeled it. So we can go ahead and say on S1, and we're looking at the paraboloid. Since the paraboloid is defined by z equals 1 minus x squared minus y squared, this is going to be my g of x. My surface is defined by this g of xy, sorry. And so now I know how to parameterize it, at least one way, and I also can conveniently produce the normal vector that I need. So my parameterization I'm going to do just in terms of x and y. I'm going to let x be x, y be y, and z, of course, is going to be g of xy, which is 1 minus x squared minus y squared. I, from my back pocket, know that r partial x cross r partial y is just negative g partial x, so negative 2x is 2x, negative g partial y, which is 2y, and then a 1. And I do want to check that this normal vector is pointing upward. So even though I didn't make this a unit normal vector, this is normal to my surface at every point. And yes, you can see the z component here is 1, so I'm gaining in the z direction. This is always going to be positive. So that's the right orientation. If I wanted to go inward, if I wanted the negative orientation, then I would just put a negative on this, and I would just change it that way. So not a big deal. You just have to pay attention to it and keep track of it. And so this parameterization, by the way, this is valid over, well, let's see, this is valid over the unit circle. How do I know that? Well, when z equals 0, I can move this part over and I get the unit circle. So this is valid on, let's just say, the unit circle, and let's just call it D. Okay, so there's my setup. And so now I'm ready to go ahead and write down the double integral over S1 of S ds1 becomes, maybe it would be helpful for us to write down what f is where we can see it too. So I'll just put it in red right here. So f is what? Y comma x comma z. And I'll need that. Okay, so I want to go ahead and write this as a double integral over the unit circle D. And I'm going to plug my parameterization into my f. And so y doesn't change, it just stays y. X doesn't change, it just stays x. But z becomes a 1 minus x squared minus y squared. Then I'm going to dot with rx cross ry. I'm going to dot with 2x comma 2y comma 1 dA. And now at this point I can work out the dot product, and so I get, let's see, a 2xy plus a 2xy, let's write it minus x squared minus y squared plus 1, whatever, I'll just change the order, dA. And so now I'm going to write this as, I'll go over here, I'm going to write this as double integral over d of what, 4xy, we'll just combine, minus x squared minus y squared plus 1 dA. I'm going to switch this thing to polar now because I know that d is just the unit circle. So when I'm thinking about the unit circle, I'm going to have r goes from 0 to 1, theta goes from 0 to 2 pi, and then I've got to plug in my polar coordinates everywhere. So let's see, 4xy, x is r cosine theta, y is r sine theta, so I get a 4r squared cosine theta sine theta. This is a minus r squared plus 1 all times r dr d theta. I invite you to pause the video and work this out. I'm not going to do it right now just to save time, and we end up with pi halves. Very doable integral. Highly encourage you to evaluate it yourself. Okay, so that's the first part of our surface. We did the surface integral over S1. Now we've got to do the surface integral over S2 and then add those together to get the full surface integral over S. And so let's think about how this is going to go on S2. So we're thinking very carefully here. We're orienting the full surface S positively, meaning outwardly. So that means on S2, I'm actually taking the downward orientation. I want the normal vectors to point down. Now, I'm going to come up with the normal vector that we need using the way that we've always done it. But I want to show you, in this case, you can see it right off the bat. Your normal vector should be minus k. It should be, we're just pointing down in the z direction. And so I can work with n equals negative k, which is just 0, 0, negative 1. Now, I'm going to come up with this the way that we always have, just so that you can see how it works. But please realize from this picture, you can see the normal vector. And that reminds me, if we scroll, instead of scrolling, I'll write it here. When we write the double integral over S2 of f dot ds2, at the beginning we said this is just f dot the normal vector ds2 with no bolding S2 anymore. And so the point is, this formula is very much in play right here. You can just dot with your normal vector and work it out. So let me show you, though, how you can derive all of this the way that we always have. So my surface is parametrized. It's defined by z equals 0. And so we can parameterize our surface by r of x and y, where x is x, y and y, and z is 0. And this is valid for, on the unit circle again, x squared plus y squared less than or equal to 1. I'll erase the word valid, even though it's fine, just to not be confusing. Okay, so let's go ahead and compute the rx cross ry, our normal vector. And, well, think about it with me. I take my equation. My defining equation was z equals 0. So my g of x, y, I usually do negative g partial x. Well, g of x, y is just 0. So negative g partial x is 0, negative g partial y is 0. And then I get a 1 by default, except that I want downward orientation. So at this point, I would use negative this. I would want to use negative rx cross ry, which is 0, 0, negative 1. Does that make sense? So you could see that coming right here from the picture, but you can also compute it using the same techniques that we already have. And so at this point, I'm ready to work out our surface integral over S2, the surface integral of f dot, the surface integral of f over S2 becomes the double integral over d being the unit circle, we'll just call that d, of, okay, plug in your parameterization, x is x, y is y, z is 0 into f. F, we said, I had written it down somewhere. Yeah, f was y, x, z, y, comma, x, comma, z. So y is y, x is x, z is 0, dot with 0, 0, negative 1, and then a dA. And now I can set up the bounds if I want to, but I'm going to go ahead and compute the dot product, and I'm going to realize, oh, wow, I just get 0 dA, which is 0. And so finally, I can say, thus, the surface integral of f over s is what we got over S1, which was pi halves, plus what we got over S2, which was 0. So the total flux is just pi halves. All right, so we'll end here, and just 2 more sections after this. We're going to learn how we can translate some of these surface integrals of vector fields into other familiar